Hello everybody. In this video, I will discuss elimination reactions, the mechanism of elimination reactions, the regioselectivity in elimination reactions, Zaytsev rule, Hofmann's rule, and stereoselectivity in elimination reactions. Here we are discussing the elimination reactions of alkyl halides. In elimination reaction, an atom or groups are removed from a reactant. See, alkyl halide usually gives substitution. You might have studied the substitution reactions of alkyl halide. Here we are discussing elimination reactions of alkyl halide. In substitution reaction, certain atoms or groups are substituted within the molecule without eliminating a group or atom. But in elimination, groups or atoms are eliminated or removed from the reactant. That is the difference between substitution and elimination reaction. Usually alkyl halides gives both the substitution reactions and elimination reactions. Okay, see, when an alkyl halide undergoes an elimination reaction, the halogen is removed from one carbon and a hydrogen is removed from the adjacent carbon to form a double bond between them, these two carbon atoms, from which these groups are eliminated, hydrogen and halogens are eliminated. Thereby an alkene is formed by this elimination reaction. Okay, just as there are two nucleophilic substitution reactions as SN1 and SN2, there are two important elimination reactions also, E1 and E2. First of all, we will discuss the E2 reaction. See, it is the example of one of the important example of E2 reaction. Here 2-bromo 2-methyl propane reacts with the base forming this alkene. In this case, the rate of reaction depends on the concentration of both the substrate molecule and the base catalyst. So it is a second order or bimolecular reaction, and hence the name E2 reaction. The rate can be represented as rate is equal to K into concentration of alkyl halide into concentration of the base. The rate law tells us that both the alkyl halide and the base are involved in the transition state of the rate determining step, indicating it is a one-step concerted reaction. E2 reaction is a concerted one-step reaction in which both the reactant, or the substrate molecule, and the base catalyst involved in the rate determining step that in this concerted mechanism. See the mechanism for E2 reaction. Here the base catalyst abstract a proton or remove a proton from the substrate molecule. At the same time, a double bond is formed in between these two carbon atoms, where the leaving group, one of the carbon atom is attached with the leaving group bromine, and the other is with a proton that is removed by or abstracted by the base catalyst. Thereby a double bond is formed in between these two carbon atoms. Thereby this alkene 2-methyl propene is formed in this reaction. That is the mechanism of E2 reaction. That is, it is a concerted mechanism. It involves both the substrate molecule and the base catalyst. First of all, base catalyst attack the beta carbon atom to abstract. It is the beta carbon atom, the carbon atom just adjacent or attached directly with this carbon atom having this leaving group, that is the beta carbon atom, and the base catalyst abstract a proton from the beta carbon atom. At the same time, this electron moved in between these two carbon atoms to form a pi bond. A new pi bond is formed between these two carbon atoms, or a double bond is formed in between these two carbon atoms. Along with or simultaneously this bromine is eliminated, or it is a concerted mechanism to form this alkene 2-methyl propane. That is the mechanism for E2 reaction. Because the elimination reaction is initiated by removing a proton from a beta carbon atom. An E2 reaction is sometimes called a beta elimination reaction also, or it is also called 1,2 elimination reaction because the atom being removed are on adjacent carbon atom. See, the halogen and hydrogen removed are from within the adjacent carbon atom, and hence it is often named as 1,2 elimination reaction. You see the general mechanism here. The base abstract proton from the beta carbon atom. It is the beta carbon atom, that is carbon atom adjacent to the carbon atom to which the bromine or halogen is attached. It is the beta carbon from which this proton is abstracted by the base. Okay, it is the alpha carbon atom, so it is beta, and from this beta carbon atom a hydrogen is abstracted by the base during the reaction. Okay, that is the mechanism. One of the important characteristics of E2 reaction is it is regioselective in nature. See, for example, an alkyl halide such as 2-bromopropane. 2-bromopropane has two carbon atoms from which a proton can be removed in an E2 reaction. Because the two beta carbon atoms are identical in 2-bromopropane, the proton can be removed equally easily from either one of the carbon atom. See, for example, it is 2-bromopropane. There are two beta carbon atoms on either side, and the proton can be removed from either of the beta carbon atoms by this base. Thereby, both the beta carbon atoms are identical. Only one alkene is formed, that is propene is formed in this case. Okay. In contrast, if we take 2-bromobutane, which has two structurally different beta carbon atoms. See, it is CH2 group and it is CH3 group. And so 2-bromobutane has two different beta carbon atoms. And from these beta carbon atoms, proton can be removed. Therefore, when this alkyl halide reacts with the base, two elimination products are formed. One is 2-butene and the other is 1-butene. 2-butene is formed by removing a proton from this beta carbon atom, and 1-butene is formed by removing proton from this beta carbon atom. So we will get 2-butene and 1-butene. Two alkenes are obtained, or two products are obtained. Among these, 2-butene is obtained at about 80%, which exists as their stereoisomers E and Z, whereas 1-butene obtained in 20% yield. And so the E2 reactions are regioselective in nature because more of the one constitutional isomer is formed than the other. Here 80% of 2-butene is formed, while 1-butene is formed only at about 20%. So the E2 reaction is regioselective in nature. See, what factor which dictate which of the two alkene is formed in greater yield, that can be discussed. See, in the transition state leading to the alkene, the carbon hydrogen and carbon bromine bond or carbon halogen bonds are partially broken and the double bond is partially formed. That is, the carbon halogen bonds are partially broken, and also carbon hydrogen bond also partially broken, and new carbon hydrogen bond is partially formed, and all these are indicated in dashed lines, that giving the transition state of the reaction, transition state of the reaction, an alkene like structure, Therefore, the factors that stabilize alkene also will stabilize the alkene like transition state of this reaction, causing the more stable alkene to be formed faster. For example, see, it is the transition state leading to the formation of 2-butene. You can see this transition state is more stable. This transition state is the transition state leading to 1-butene. It is less stable. You can see there are two methyl groups on either side of carbon-carbon double bond, or this sp2 carbon atom containing one methyl group each in the case of transition state leading to 2-butene, whereas the sp2 carbon of this transition state having only one alkyl group that is directly attached to this sp2 carbon, that is ethyl group, only one ethyl group. Here each of these two sp2 carbon which is attached with the methyl group. You can see both the sp2 carbon containing methyl group, and hence this methyl group with hyperconjugation or plus inductive effect will stabilize more of this transition state than this transition state which containing only an ethyl group on one of the sp2 carbon only. That is why it is less stable and it is more stable. This transition state is more stable because each of the sp2 carbon containing one methyl group having plus inductive or electron releasing effect, that is hyperconjugative effect and also plus inductive effect, whereas in this transition state only one of the sp2 carbon containing alkyl group, that is ethyl group, and hence this transition state is more stable than this transition state, and hence 2-butene with the 2 methyl substituent bonded to its sp2 carbon is more stable than 1-butene with one ethyl substituent. Thus 2-butene is the major product. That is the reason why 2-butene is formed as the major product than is the major product in the case of this elimination reaction. This is another example of unsymmetrical alkyl halide which having two beta carbon atom, different beta carbon atom, which on treating with base forming two alkenes, not a single alkene. Instead we get two different alkenes. One is more substituted and other is less substituted. The more substituted 2-methyl 2-butene is formed as the major product. About 70% of 2-methyl 2-butene is obtained by this reaction. See, all this or the formation of the more substituted product alkene as the major product is governed by an important rule which is called the Zaytsev rule. You know, Zaytsev rule. What is Zaytsev rule? Zaytsev rule, according to Zaytsev rule, when elimination takes place in an unsymmetrical alkyl halide, eliminating groups are eliminated in such a way that more substituted alkene is obtained as the major product. That is Zaytsev rule. That is, the formation of more substituted alkene from an unsymmetrical alkyl halide on elimination is governed by Zaytsev rule. According to Zaytsev rule, when elimination takes place in an unsymmetrical alkyl halide, eliminating groups are eliminated in such a way that more substituted alkene would be the major product. See this example also. It is 2-chloropentane, an unsymmetrical alkyl halide, which having two beta carbon atoms on either side of this carbon atom attached with the halogen. You can see the right side carbon atom containing 3 beta hydrogen atoms and the left side carbon atom containing 2 beta hydrogen atoms, which on treating with a base catalyst, for example methoxide ion, two alkenes, different alkenes are obtained. Among these, the more substituted or the disubstituted alkene here, it is 2-pentene, is obtained as the major product. About 67% of 2-pentene is obtained, whereas 1-pentene, it is the less substituted alkene, that is only mono-substituted, it is obtained about 33% only. This 2-pentene actually obtained as the mixture of E and Z isomers and is obtained about 67 percentage, the major product. Usually, the major product of an E2 reaction is generally the more stable alkene. More stable alkene. That would be usually more substituted alkene. There are some limitation for Zaytsev rule because the more substituted alkene is not always the more stable alkene. For example, see this reaction. It is an alkyl halide which containing a double bond, which on treating with the methoxide, we will get two dienes. One of the diene is a conjugated diene and the other is isolated diene. The conjugated diene is obtained as the major product. Even though it is less substituted, it is obtained as the major product. The isolated diene, which is more substituted. This double bonded carbon containing two methyl group and this double bonded carbon containing this alkyl group. Even though it is obtained as the minor product, whereas the conjugated diene is obtained as the major product. It is because this conjugated diene is more stable than this isolated diene, and hence even though it is less substituted, the conjugated diene is obtained as the major product. Okay, in such cases Zaitsev rule is not valid. Okay, similarly see this example. This alkyl halide containing this beta carbon atom attached with a phenyl ring or benzene ring, which on treating with the base catalyst, forming two dienes. One is with the conjugated double bonds. You can see double bond, single bond, double bond of benzene ring. And so the double bond is conjugated with the benzene ring. It is obtained as the major product, while this isolated diene, which is not conjugated, obtained as the minor product. And so in this case also Zaitsev rule is not valid. So it is because Zaitsev rule cannot be used to predict the major product of the foregoing reaction because it does not take into account of the fact that conjugated double bonds are more stable than isolated double bond. Therefore, if the alkyl halide has a double bond or a benzene ring, do not use Zaitsev rule to predict the major product of the elimination reaction. See, if the base in an E2 reaction is bulky and its approach to the hydrogen, beta hydrogen, that leads to more stable alkene is sterically hindered, it will preferentially remove the most accessible hydrogen. Therefore, the major product is less stable alkene. Okay, for example, see this example. It is the bulky base, tertiary butoxide is a bulky base. When it approaches this bulky alkyl halide, it approaches only the less accessible, or the more accessible hydrogen. These two methyl group hydrogen or hydrogens of this methyl group are more accessible than hydrogen of this CH2 group because it is sterically hindered. This hydrogen is sterically hindered with this methyl group and this bulky tertiary butyl group, and hence these hydrogens of methyl group are more accessible, and hence this bulky tertiary butoxide, the base catalyst, approaches only the more accessible hydrogens of methyl group, and hence we get the less stable alkene as the major product. It is the less stable alkene, less substituted alkene will be obtained as the major product in this case when bulky base is used for elimination reaction of bulky alkyl halide. If the alkyl halide is not sterically hindered and the base is not moderately hindered, the more stable alkene will be the major product as expected. So, for example, in the case of 2-iodobutane, even though it is tertiary butoxide, a bulky base catalyst, we will get more stable alkene or more substituted alkyl as the major product because it is moderately sterically hindered. Even though this tertiary butoxide is bulkier, we will get the more stable or more substituted alkene as the major product. 2-butene here obtained as the major product, while the 1-butene is obtained as the minor product. Okay, the Zaytsev rule is also not valid in the case of elimination reactions in alkyl fluoride. Alkyl fluoride preferentially form less stable alkene. See, although the major product of E2 reaction of alkyl chloride, alkyl bromide, and alkyl halide is normally more stable alkene, the major product of E2 reaction of alkyl fluoride is less stable alkene. See, for example, it is 2-fluoropentane, which on treating with the methoxide, the base catalyst, we will get 1-pentene, the less substituted alkene, obtained as the major product. About 70% of 1-pentene is obtained, whereas 2-pentene, which is more substituted and more stable, it is obtained only about 30% yield. When a hydrogen and a chlorine, bromine or iodine are eliminated from an alkyl halide, the halogen starts to leave as soon as the base begins to remove the proton. Consequently, the transition state resembles an alkene. Both the process taking place simultaneously. But in the case of alkyl fluoride, the fluoride ion, however, is the strongest base of the halide ions and therefore the poorest leaving group also. So, when a base begins to remove a proton from an alkyl fluoride, fluorine does not have a strong propensity to leave as another halogen would have, as chlorine or bromine or iodine. As a result, a negative charge develops on the carbon that is losing the proton, causing the transition state to resemble a carbanion rather than an alkene. Okay, see, it is the carbanion like transition state leading to the formation of 1-pentene, and it is the carbanion like transition state leading to the formation of 2-pentene. You know, this carbanion like transition state is more stable than this carbanion like transition state because this carbanion, it is a primary carbon. The negative charge is on the primary carbon atom. Whereas in this case, the negative charge is on the secondary carbon atom. You know, the primary carbanion is more stable than secondary carbanion. And so secondary carbanion, this transition state is less stable because it is secondary carbanion. It is less stable than primary carbanion. This transition state leading to 1-pentene, which is more stable, you know, the transition state is more stable, and hence 1-pentene is obtained as the major product rather than 2-pentene because the transition state leading to the formation of 2-pentene is less stable because the carbanion is secondary carbanion. Okay, by excluding these exceptional cases, generally the relative reactivities in an E2 reaction can be explained as, you know, because the elimination from a tertiary alkyl halide typically leads to a more substituted alkene than does elimination from secondary alkyl halide, and because elimination from a secondary alkyl halide generally leads to a more substituted alkene than does from a primary alkyl halide, the relative reactivities of alkyl halides in an E2 reactions are tertiary alkyl halides greater than secondary alkyl halide, which in turn greater than primary alkyl halide. So, see this alkyl halides. It is tertiary alkyl halide forming a more substituted alkene which having 3 alkyl substituents. And in the secondary alkyl halide, it is an example of secondary alkyl halide leading to the formation of 2 alkyl substituents, leading to the formation of alkene with 2 alkyl substituents. Whereas in the case of primary alkyl halides, which on elimination leading to the formation of an alkene with 1 alkyl substituents. Okay, now let us consider even reaction and its mechanism. The second kind of elimination reaction that an alkyl halides can undergo is an even reaction, where E stands for elimination and 1 stands for unimolecular or monomolecular. See, for example, this 2-bromo 2-methyl propane. It is a tertiary alkyl halide. On treating with water acts as a solvent, forming an alkene 2-methyl propene. The rate of an even reaction depends only on the concentration of alkyl halide, not on the base catalyst, only on the concentration of alkyl halide, and hence it is unimolecular reaction. See, the rate of reaction that can be represented like this. Rate is equal to the rate constant K into concentration of alkyl halide. Okay, see the mechanism of even reaction. Here 2-bromo 2-methyl propane decomposes or heterolysis of this carbon halogen bond takes place in the rate determining slow step, forming a more stable carbocation as in SN1 reaction. Here bromine gets eliminated to form this tertiary butyl carbocation. Then the base, here it is solvent water, removes a proton from the beta carbon atom, forming a carbon-carbon double bond between these 2 carbon atoms, or beta elimination takes place to form this alkene 2-methyl propane. So the mechanism is monomolecular because only the substrate molecule alkyl halide take part in the rate determining slow step, where carbon halogen bond, the heterolysis of carbon halogen bond take place to form a carbocation. And then in the next step, which is the fast step, the solvent capture a proton from the beta carbon atom to form alkene, corresponding alkene. That is, in this case, it is 2-methyl propane. That is the mechanism of the reaction. The alkyl halide dissociates first, forming the carbocation. Then the base forms the elimination product by removing the proton in the fast step from the beta carbon atom. Here, because the first step is the rate determining step, an increase in the concentration of the base, which participates only in the second step of the reaction, has no influence upon the rate of the reaction. Generally, in the even reaction, the solvent is the base. We are using solvent for the even elimination reaction. Here water acts as a solvent and take part in even elimination reaction of this alkyl halide. Okay, see, similar to E2 reaction, even reaction is also regioselective. That is, when more than one alkene can be formed, the even reaction like E2 reaction, the major product obtained will be the more stable alkene. That means even reaction is regioselective in nature. For example, see, it is 2-chloro 2-methyl butane, 2-chloro 2-methyl butane, which on solvolysis with water, elimination reaction takes place to form this 2-methyl 2-butene and 2-methyl 1-butene. 2-methyl 2-butene, which is more stable alkene, is produced as the major product. Okay, because the rate determining step of an even reaction is carbocation formation, the rate of an even reaction depends both on the ease with which the carbocation is formed and how readily the leaving group leaves. That is, the rate determining step is the formation of carbocation, and any factor that increase the formation of possibility of formation of carbocation increases the rate of reaction. Okay. Therefore, tertiary alkyl halide which readily undergo even reaction because they form relatively stable carbocation. Then primary and secondary alkyl halide do not undergo even reaction because their carbocations are less stable and because high concentration of base, in this case it is solvent, are used in these reactions, both of which increases the fraction of reaction that takes place by an E2 pathway. Here we are using the solvent as the base catalyst. As the concentration of the base catalyst solvent increases, the fraction of the reaction that takes place in the E2 pathway will increase. So, primary and secondary alkyl halides do not undergo even reaction in normal case. Okay, because their carbocations are less stable. Okay, therefore, primary and secondary alkyl halide undergo only E2 reaction. Right. Notice that the same bonds are broken and formed in both the E2 and E1 reaction. The only difference is the timing. That is, the proton is lost in the first step of an E2 reaction and it is lost in the second step of an E1 reaction. See, that is the main difference. But the same bonds are broken and formed in both the E2 and E1 reaction. Thereby, there will be a competition between E2 and E1 reaction. We saw the primary and secondary alkyl halide undergo only E2 reaction. Primary and secondary alkyl halide only undergo E2 reaction. Because of the relative unstable carbocation, they form unstable carbocation and the presence of large concentration of base in the solvent is this reaction. Thereby, primary and secondary alkyl halide usually undergo E2 reaction. But tertiary alkyl halide undergo both the E2 and the E1 reaction. Tertiary alkyl halide undergo both E2 and E1 reaction. Notice that a tertiary alkyl halide and a strong base, that is a requirement, were chosen for the E2 reaction, whereas tertiary alkyl halide and a weak base were chosen to illustrate E1 reaction. Okay, you know, E2 and E1 reactions are stereoselective in addition to their regioselective. See, in addition to being regioselective, that means more than or more of one constitutional isomer is formed than the other. E2 and E1 reactions are stereoselective also, meaning that more than one stereoisomer is formed than another. Because an E2 reaction is concerted, the bonds to the groups to be eliminated must be parallel. Because the sp3 orbitals of carbon bonded to hydrogen and the sp3 orbitals of carbon bonded to halogen become overlapping p orbitals in the alkene product. For maximum overlap in the transition state, the orbital must be parallel. There are two ways in which carbon hydrogen and carbon halogen bonds can be parallel. They are eliminating groups. Hydrogen and halogens are, eliminating groups. They can be either on the same side of the molecule or on the opposite side of the molecule in order to become parallel. In an elimination reaction, removes two substituents from opposite sides of the molecule. It is called an anti-elimination. Whereas if the substituents are removed from the same side of the molecule, the reaction is called syn elimination. See, both the types of elimination can occur, but anti-elimination, that is, remove the substituents from opposite side of the molecule, is highly favored in an E2 reaction. Soh's projection. See the Soh's projection of these elimination reactions, which show the carbon bond from an oblique angle, reveal why this is true. See, it is the anti-elimination where the base attacks the proton of the beta carbon atom as backside attack or from backside. It is more favored staggered conformation. It is most favored staggered conformation whereby a backside attack of base in order to capture the proton from beta carbon atom is possible. But in syn elimination, the hydrogen, the leaving groups are in eclipsed conformation. It is less favored conformation, whereby the base forced to attack the hydrogen or forced to capture the proton from the front side, or only the front side attack is possible in eclipsed conformation or syn, or in the case of syn elimination. See the eclipsed conformation of hydrogen in the beta carbon atom and halogen, they are leaving groups, and these leaving groups are oriented in eclipsed conformation in syn elimination reaction, whereby the base attack is only possible from front side. Okay, that is why in E2 reaction the anti-elimination is more favored. That is, for anti-elimination, the eliminating groups are anti to each other. That means they are in more favorable staggered conformations, whereby base can attack the proton from backside. That is why anti-elimination is highly favored in an E2 reaction. Anti-elimination requires the molecule to be in a staggered conformation, whereas syn elimination requires it to be in a less stable eclipsed conformation. It is less stable eclipsed conformation, that is in the syn elimination, where the departing groups are in the less stable eclipsed conformation, whereas in anti-elimination they are more favorable, they are in a more favorable staggered conformation. In an anti-elimination, the electrons of the departing hydrogen move to the backside of the carbon to halogen. You can see this carbon hydrogen bond. The electron of this departing hydrogen move to the backside of this carbon, which is bonded to this halogen. Whereas in syn elimination, the electrons move to the front side of the carbon, which is bonded to hydrogen. We saw that displacement reactions occur through backside attack. Usually the displacement reaction occur through backside attack because that is how the interacting orbitals can achieve the best overlap. In anti-elimination, the electron-rich base is spared the repulsion, or it can avoid the repulsion that it may experience when it is on the same side of the molecule. That would be the case in the syn elimination as the electron-rich departing haloid ion. Okay, an E2 reaction is usually stereoselective. That means more of one stereoisomer is formed than the other. For example, the 2-pentene obtained as the major constitutional isomer from E2 reaction of 2-bromopentane is actually a pair of stereoisomers, and more of E2-pentene is formed than Z2-pentene. You can see it is 2-bromopentane, which on E2 reaction we will get two alkyls. One is E2-pentene, where the bulky groups are on the opposite side of the double bonds, carbon-carbon double bond, which is obtained as the major product. While Z2-pentene, you can see the bulky groups are on the same side of the carbon-carbon double bond in Z2-pentene, which is obtained as the minor product. Here you can see this beta carbon atom having two hydrogen atoms. Thereby it will give two products. Either of this hydrogen atom may be removed, and thereby two products are formed. One is E2-pentene, while the other is Z2-pentene. Among these, E2-pentene, where the bulky groups are on the opposite side, thereby the steric strain or steric hindrance may be minimized, will be obtained as the major product. That is, if the reactant has two hydrogens bonded to the carbon from which a hydrogen is removed, both the E and Z products will be formed because the reactant has two conformers in which the groups to be eliminated are anti. That means if the reactant has two hydrogen bonded to the carbon, we will get two alkyls. One is obtained as E product while the other is obtained as Z product. If there are two hydrogens bonded to the carbon from which a hydrogen is removed within an alkyl halide, similar to 2-bromopentane. Okay, see, these are the two conformers of 2-bromopentane in which hydrogen and bromine are anti. In this conformer, this bromine and the hydrogen on the next carbon atom, beta carbon atom, are anti. It is one of the conformer. And another conformer where the bromine and hydrogen are anti to each other is this conformer. You can see in this conformer the bulky groups are on the opposite sides of each of the carbon atom, whereas in this conformer the bulky groups are on the same side of the carbon atoms, adjacent carbon atoms. That is the difference between these two conformers where the hydrogen the departing groups hydrogen and bromine are anti to each other. From this conformer, after the elimination, we will get E2-pentene, which will be more stable because these bulky groups are on the opposite side of the carbon-carbon double bond, whereas this Z2-pentene, which is formed from this less stable conformer, even though this hydrogen and bromine are anti to each other, that is favorable condition for E2 elimination. These bulky groups are on the same side of carbon atoms, and hence the Z2-pentene formed from this conformer is usually less stable because these bulky groups are on the same side of the carbon-carbon double bond. Okay, that is stereoselectivity. That means one of the stereoisomer will be obtained as the major product. Here E2-pentene will be obtained as the major product from 2-bromopentane. That is stereoselectivity in E2 reaction. Okay, that is why in this elimination reaction we get this alkene obtained as the major product. It is E-alkene, where this tertiary butyl bulky tertiary butyl group and this methyl group are on the opposite side of the carbon-carbon double bond. It is the E product which will be obtained as the major product in the elimination, in this elimination reaction, whereas the minor product obtained is this alkene, where this bulky group, the tertiary butyl group and this methyl group are on the same side of the carbon-carbon double bond. This indicates the stereoselectivity of E2 reaction. Okay, if however the beta carbon atom from which a hydrogen is to be removed is bonded to only one hydrogen, then there is only one conformer, in contrast to the E2 elimination where the beta carbon atom from which two hydrogen atoms are to be removed, as we discussed earlier. Here, if the beta carbon atom from which a hydrogen is to be removed is bonded to only one hydrogen, then there is only one conformer in which the group is to be eliminated or anti, only one chance in which the hydrogen and the halogen to be anti or eliminated groups are hydrogen and halogen which are to be anti. Only one conformation is possible. Therefore, only one alkene product is formed. The particular stereoisomer formed depends on the configuration of the reactant. For example, anti-elimination of HBr from 2s, 3s, 2-bromo, 3-phenyl butane forms only the E isomer. You can see 2s, 3s, 2-bromo, 2-phenyl butane. It is this molecule 2s, 3s, 2-bromo, 3-phenyl butane, which on elimination reaction with this methoxide ion, it capture proton from the beta carbon atom. See this carbon atom having only one hydrogen, and which will have only one conformer to be anti to bromine. So it is the anti-conformer of this molecule which having beta carbon atom with one hydrogen only. And so we get only one product, that would be E2-phenyl 2-butene. E2-phenyl 2-butene. Whereas the elimination of hydrogen bromide from 2s3r 2-bromo 3-phenyl butane, it forms Z isomer. See, it is Z isomer. Here you can see the phenyl group and the methyl group are on the same side in this isomer, whereas in this isomer the phenyl group and methyl group are in trans to each other. In the conformation, in this conformation, this phenyl group and methyl group are trans to each other, whereas in this conformation or in this isomer, this phenyl group and methyl groups are cis to each other, or it is 2s3r 2-bromo 3-phenyl butane, where this hydrogen and bromine are anti to each other, and from this isomer we will get to Z2-phenyl 2-butene. But here we get E2-phenyl 2-butene if we use 2s, 3s, 2-bromo, 3-phenyl butane. See, an even reaction like an E2 reaction is also stereoselective. And like E2 reaction, both E and Z products are formed, and the major product is the one with the largest group on the opposite side of the double bond, as in the E2 reaction. We know that an even reaction takes place in 2 steps. The leaving group first leaves in the first step, and a proton is lost from an adjacent carbon atom in the second step, following Zaytsev rule for forming the more stable alkene. The carbocation created in the first step is planar, so electrons from a departing proton can move towards positively charged carbon from either side. Therefore, both syn and anti-elimination occurs. See this reaction. Here beta carbon atom has one hydrogen. It is the beta carbon atom with respect to this carbon, which having only one hydrogen atom, which on treating with ethanol, the solvent, even reaction takes place to form first the more stable tertiary carbocation, and from this proton is removed to form these 2 products. One is E3,4-dimethyl 3-hexene, which is obtained as the major product because you can see the bulky groups are on the opposite sides of the carbon-carbon double bond. Then another is Z3,4-dimethyl 3-hexene, which will be obtained as the minor product because these bulky groups are on the same side of the carbon-carbon double bond. Okay, that is stereoselectivity in even reaction, similar to E2 reaction. One important point to be remain in your mind, because both syn and anti-elimination occur in an even reaction. Both syn and anti-elimination occur in even reaction. See, in the case of E2 reaction, only anti-elimination takes place. That is the favorable elimination reaction condition for elimination in E2 reaction. While both syn and anti-elimination occur in an even reaction. Both E and Z products are formed regardless of whether the beta carbon from which the proton is removed is bonded to 1 or 2 hydrogen. Here both the E and Z isomer are obtained because both syn and anti-elimination occur regardless of whether the beta carbon from which the proton is removed is bonded to 1 or 2 hydrogens. Here both the isomer E and Z isomer are obtained. But the major product is one with the largest group on the opposite side of the double bond, because that is more stable alkene and therefore it is formed more rapidly. That is the stereoselectivity in even reaction. Here one of the important point is both syn and anti-elimination occur in an even reaction, and so both E and Z products are obtained, regardless whether the beta carbon from which the proton is removed is bonded to one or two hydrogen. But the major product will be one with the largest group on the opposite sides of the double bond, as in the E2 reaction. But in E2 reaction, only the anti-elimination occur. Okay, so we had already discussed the E2 reaction, its mechanism, its regioselectivity, stereoselectivity, then even reaction, the mechanism of even reaction, the regioselectivity of even reaction, and the stereoselectivity in even reaction. I think you might have understand all these concepts. I hereby conclude this video here. Thank you so much for watching this video. Thank you.